All right, here on the left, I have a convex mirror, which means it's bowed out, and on the right, a concave mirror, which means it's caved in. Sometimes we use the words converging and diverging. Now, when we're talking about mirrors, diverging means to spread apart. So if you think of Robert Frost, two roads diverged in a yellow wood, then what that means is any ray that's going to come in is going to shoot outward, because the rays are going to be spreading apart. All parallel rays are going to be spreading apart as if they came from the focal point, which looks like it's back behind the mirror. So we say that they make virtual images because the image looks like it's back behind the mirror. I look like I'm back there. Now in the mirror on the right, the concave mirror, we call that converging because it's bringing light rays together. Parallel rays come together at the focal point, and so it can make both real and virtual images. So right now, what you're seeing is a real image of me, and you see how it looks like I'm upside down? And you might think, well, everything is upside down and real in a concave mirror. But that's not true, because look at me. I'm right side up, and I'm huge. But wait, now I'm upside down, and I'm real. No, I'm right side up, and I'm virtual behind the mirror. No, I'm upside down, and I'm on your side of the mirror. So concave mirrors can do both, and we're going to talk about why that is. Right, we're going to talk about ray diagrams to figure out where the images are formed for mirrors, and we're specifically looking at concave mirrors here, which are a type of spherical mirror. The reason that they're called a spherical mirror is because it's kind of like a section of a sphere. So I'm just going to do it like a side profile here, and you can see that if this were a great big circle, not very circular, the center of the circle would be like right there. Okay, so here's my mirror, and it's a concave mirror, which means that it's caved in, and this is the center of curvature. Right, so if we follow the law of reflection, any line that comes to a circle or a sphere from the center, that's called the radius, right? And that hits at 90 degrees to a line tangent to that point. So if it hits at 90 degrees, we say it's normal to the mirror. Normal is another way to say perpendicular or 90 degrees. All right, well, if you remember the law of reflection, this is important if you play pool, especially if you play pool with round bumpers, which I think there is a game like that, like snooker or something. Anyway, if a ray comes in from the center, according to the law of reflection, the angle it comes in at is the angle it's going to go back at. So it will go right back through the center. If a ray comes in parallel, it's going to bounce back at a point halfway between the mirror and the center. Halfway. Oh, there it is. Halfway between the mirror and the center. All right, that's because the angle of incidence, so this is the incoming angle, incidence is a science word for incoming, needs to equal the angle of reflection. Now, I measured those angles with the mirror, and that's fine to do, or you can measure it with this line, which is a line perpendicular to the mirror. We call that the normal. So the angle of incidence needs to equal the angle of reflection. Right, so as we make our drawings, we're going to keep that in mind, that any ray that comes into a spherical mirror from parallel to this line right here, which is called the principal axis, the line right through the center of the mirror, any ray that comes in from parallel will bounce back through this point halfway to C, which is called the focal point. So you've heard of the focal point? All parallel rays for a concave mirror are going to bounce back through that focal point. So you can imagine that it's a solar collector. You're taking parallel rays, and bouncing them back through the focal point. So you can see that all rays that come in from parallel are going to bounce back through the focal point. So you're going to be getting a whole bunch of rays here. Any rays that come in from C are going to bounce back through C. No matter where they go, if they hit the mirror and they come from C, they're going to bounce back through C. So C is twice F, or F is half of C. And F is the distance from the focal point to the mirror. So a more curved mirror will have a shorter focal point. Okay, here I'm using a concave mirror to collect rays from the sun. It's in the evening, so the sun's kind of low, but the rays are coming from so far away. They're like all these parallel rays coming, and it's going to bend them to the focal point. So I want to put the paper where I get a real bright spot on the paper, and then I know that the paper is at about the focal point. You can see that even though black is absorption of all color, it's real bright in the paper. And call the fire department! All right, so based on the rules that we learned, I want to talk about why one time I was upside down and another time I was right side up. So let's just say that that's the focal point right there. And let's say that I was somewhere far from the mirror. This little arrow is going to represent me. Anything below this line, which we call the principal axis or the optical axis, anything below that line is going to be what we call upside down. So here I am. All right, the reason that you can see me right now is because light from this room is reflecting off of me. I'm not transparent. I'm an object that reflects light. I absorb some, but I reflect a lot of light, and you see the reflected light. I'm not radiating light either. But most objects either radiate light or reflect light, and that's why you can see them. So we'll represent the object with an arrow. This is the object. Okay, so light comes from it. Now there's about an infinite number of rays, but I am just going to worry about a few, because if I know where a few go, anytime that rays intersect, there's an image there. So a ray will come from this parallel, right? We just talked about where that's going. It's going to bounce off the mirror back through F, right? By the same math, the angle of incidence equals the angle of reflection. A ray that comes from F is going to bounce back parallel. So you can see that here I am on my side of the mirror upside down. That's the image. It happens to be about the same size. That's because I'm at about twice the focal length, right? If I was closer, I would be getting bigger, but it's on my side of the mirror and it's upside down, right? But what if I decided I want to stand really close to the mirror, somewhere inside of F, and then try the same trick, right? So here comes a ray parallel to the mirror. Where is that going to bounce? Back through F. How about a ray that was coming from F? Right? When I say coming from F, I'm not talking about actually coming from F. I'm talking about coming from an angle, as if it was coming from F. Well, that's going to hit the mirror, and it's going to bounce back parallel. Parallel to what? Parallel to this thing called the principal axis. Right? Do you think that these two rays, ray number 1 and ray number 2, are about to intersect somewhere on my side of the mirror? I don't. They're actually getting further apart. So as they come back to me and hit my eyes, I say to ray number 1, where are you coming from? And it seems to be coming from the great beyond. No, that's not right. Something like that. And then I say to ray number 2, where are you coming from? And it seems to be coming from like there somewhere. And so that is the image. Now that's virtual, because it's not on my side of the mirror. Light rays are not really converging like they were here. Light rays were coming together. This is where light rays appear. I should actually be drawing dashed lines. This is where light rays appear to be coming from back behind the mirror. And this is right side up and larger. Here I was upside down, and maybe just a smidge smaller, but this is real. This is a real image because it can be projected, it's out in space, it's not behind the mirror, and so it's real. All right, this is a convex mirror, so I want to show you why convex mirrors do what they do. They're not as exciting as concave mirrors, but this line through the center, we've called that the principal axis, and it's important to always draw that when you're making a ray diagram. And then you're going to put the focal point in. Now this mirror happens to be curved about some center over here. So halfway to that is the focal point. So if I'm over here on the real side of the mirror, And I just call this the object because this is where the light rays are coming from. And light's coming from me to the mirror when a light ray hits the mirror coming from parallel. And when I say parallel, I mean parallel to the principal axis. So this is one ray that I'm investigating. What's that going to do? It's going to fly outward as if it came from F. It didn't really come from F, but it looks like it's coming from F. Really what happened is light hit this mirror and bounced outward, just like a pool ball would do if it hit a bumper like this. Okay, we call that diverging when light rays spread apart. So this is a diverging mirror. So this is going to be ray number 1. Okay, let's do another ray. We could investigate many different rays, but we just need to know about a couple of them. So I'm going to head at F, heading at F. See how I was heading right at F? I would have hit it if I kept on going. But I didn't because I hit a mirror. And now the rule says you will bounce back parallel. It's like geometry, like the law of reflection. The angle that it comes in at with the mirror equals the angle that it goes out at with the mirror. Really struggling to draw a straight line. I don't know why. But that's pretty close. Okay, we'll call that ray number 2. And so if you look at my 2 reflected rays, the bounce back rays, see how they are getting further apart? That means they're not about to intersect. So there's not going to be any real image made today. Sadly, convex mirrors don't do that. But if I were to trace these 2 rays back and say, where are you coming from? Well, I already know where number 1 is coming from, but if I trace number 2 back, it looks like it's coming from right there. So we see a point of intersection. In other words, if I think of these 2 rays as the 2 coming flying off the mirror, these 2, I would have to conclude that there must be something back there that they're coming from, something back behind the mirror. And that's what makes it a virtual image. And it's always right side up, so it's upright and virtual. But an even more important thing, with a convex mirror, it's always smaller. So this is me, but this is the me I see. It's always smaller. So this is a little trick for you. If you're ever gonna eat some soup, you don't wanna make a mess and you're like, is this the right side of the spoon? Or is this the right side of the spoon? Well, the convex side, if you look at yourself, you'll be right side up and smaller. And then you'll know, don't eat with that side. Because on a concave side, I'll be upside down. Because that's gonna make a real image, which is upside down. I can use concave mirrors to make it look like there's a hologram. It's almost like the image of the frog is floating there above the opening somehow. But if I look down in there, you can see that the frog is really just sitting in the bottom on a concave mirror. And there's nothing really there, but it appears to be floating in midair.